Hey everyone, and welcome back to the channel. In today's video, we're gonna dive into a super exciting topic, building a self-evolving genetic algorithm in Python. I know that sounds complicated, but trust me, by the end of this video, you will understand exactly how it works and how to make your own genetic program. Whether you are a Python beginner or someone looking to develop your coding skills, this project is for you. So let's get started. The first step is what is a genetic algorithm. Before we dive into the code, let's quickly understand what a genetic algorithm is. It's an algorithm inspired by natural selection, the process that drives evolution. Just like in nature, the fittest individuals survive and reproduce. Over time, the population evolves and gets better at solving problems. In our case, we will use a genetic algorithm to evolve a solution for calculating Fibonacci numbers. The program will start with random attempts and improve itself over time until it can correctly generate the Fibonacci sequence. So the second step is understanding the problem, which is Fibonacci sequence. Let's first take a quick look at the Fibonacci sequence. It's a series of numbers where each number is the sum of the two preceding ones. So it starts with 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. So we wanna evolve a program that can calculate Fibonacci numbers. Our genetic algorithm will help us evolve this program to get the correct Fibonacci sequence. The next step is setting up your development environment. Before we jump into coding, make sure you have Python installed on your computer. You don't need any special libraries. Just Python's built-in features will be enough for this project. I am using Visual Studio Code, but you can use any text editor you like. All right, let's assume you have uh, setting up your development environment, and let's jump into the next step. The next step is generating the initial population. As you've seen in the uh, diagram, the first step is just generating initial populations. Any assumption, you can randomly generate between ranges. And the next step is selection. You can select from the initial populations, and there will be implementing crossovers and mutation. Then finally we get the better solution. Okay, so now let's implement the generating the initial population algorithm. Let's start coding. The first thing we need to do is generate the initial population. In our genetic algorithm, the population represents a group of solutions. Each solution will be a program that tries to calculate the Fibonacci numbers, but this will be random at first. So you first import a random library. This library will help you to generate random initial populations. All right, let's generate the population of random solutions. This function will take two parameters, the population size and maximum length of the genes. Now let's define an empty list that's going to store the genes of each individual. In this case, we are going to iterate through the population size and then generate random genes for each population. For a population in a range of pop size, then now let's generate random genes for each population. Random dot rand int function that could help us to generate, for example, 0 up to 10 for every uh, number in the range of maximum length. All right, so this will be the random genes of each population. Now we are going to append the individual genes, list of individual genes into the population. And the function going to return the population. Right, let's run this code to make sure that it's working fine. Okay, so this generates population function takes two parameters, pop size and max length. This function generates a population of size pop size where each individual has a list of random genes, and we use random dot rand int to pick a random number between 0 up to 10 for each gene. The max length is the length of the individual solution. Basically, how many numbers our Fibonacci program will try to generate. All right, next, we are going to create a function that's used to measure how good a solution is. In our case, it will compare each solution to the correct Fibonacci sequence and give it a score based on how many numbers match. So in this case, we define a function, fitness function, and this function measures how accurate the Fibonacci sequence is. Okay, so this Fibonacci fitness function take individual genes as an argument, and here we are going to just define the correct Fibonacci sequence numbers. For example, 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. All right, this is correct Fibonacci number. Now we are going to define a variable score that's going to store the score of the fitness function, how a good solution is. Now we iterate through length of the Fibonacci sequence, and okay, and here we predict the individuals. There is a predicted variable that's going to predict individual genes for every Fibonacci sequence number. Okay, this is just an example. You can replace with real calculation. Okay, so now we are going to compare the predicted value of each individual and Fibonacci sequence of at the same position. Okay, I because the predicted value is the individual gene at the position of the Fibonacci sequence, and we compare that predicted value with the Fibonacci sequence at the same position in the Fibonacci sequence numbers. Okay, now if that is equal, we are going to increase the score by 1. And finally, this function going to return the score of the fitness. Okay, all right, let's run, and yeah, it's correct. So here we define the correct Fibonacci sequence numbers, and we then compare Fibonacci uh, numbers generated by each individual to the actual sequence. If the predicted number matches the correct Fibonacci number, we increase the score by 1. Then the higher the score, the better the individual solution is. Okay, all right. Next, selection process. Now that we have a way to measure fitness, we need a selection process. The idea is to pick the best solutions, that is the fittest one, to reproduce and pass on their genes to the next generation. So now let's define a function that's going to select two individuals based on the fitness score we have defined here. Okay, select parentheses and this takes population, and the population sorted is population. Here we are going to just uh, get the highest score from the fitness. In this case we are going to use the lambda that's take for each fitness score and attach to the population, and finally we are going to just uh, return the highest scores of the population. Okay, lambda x fitness, here we pass that x and we just reverse is true in the reverse direction because the highest score could be in the top. Now let's return the population at index 0 and 1, because here we take two parentheses. We select two individuals based on the fitness score, so we have the first individual and the second individual, and here population 1 at index 1. Okay, let's run and continue to the next. Okay, so here the select parents function just sort the population by fitness using the sorted function, where the best solution comes first, then we return two best individuals, parents to reproduce. Okay, and the next step is crossover and mutation. Next, we need crossover and mutation. These are two main processes that drive evolution. The crossover mixes genes from two parents to create a new solution, and the mutation introduces random changes in the offspring to ensure variety. Okay, let's define a function crossover to create offspring. So this take parent one and parent two. The parent one and parent two are generated here or selected here based on the fitness score. Okay, so in this case we define a variable crossover point and take the length of the half of the parent one here, then parent one and divided by 2, integer division, because we the crossover is the point, integer point, and it just assign the half of the parent one, the length of the parent one, and there could be child wherever you parent their child, and they take the half of the parent one crossover point, uh, and parent 2. Okay, here, so the child just the combination of the half of the parent one and the parent 2. Okay, and now let's return the child. Okay, that's fine. Next, let's mutate an individual by changing a random gene. Here we just calculate the mutation point. The mutation point is a random integer number from 0 up to the total length of individuals. Okay, 0 up to the length of individual. Here we subtract 1. Okay, so now we just mutate or randomly change individual, then take the mutation point. Here it could be an underscore, and here just randomly mutate rand int from 0 up to 10, and finally it's going to return individual. All right, so we cut both parent 1 and parent 2 into half of, and combine the first parent or parent 1 with the second parent 2 to create a child, and it returns the child. Then we randomly pick one gene from the individual and change it to a new random value. Okay, this mutation helps keep the population diverse. Now let's run and continue to the next. Okay, now that we have all the pieces in place, we can put everything together into the main loop where we evolve the population. Over multiple generations, the solution should improve as they learn from each other. So here we are going to define the genetic algorithm that combines all functions together and that perform the genetic algorithm or evolving solution of the Fibonacci sequence. Okay, the main genetic algorithm function. So this genetic algorithm take parameters, the population size, the generations, and the max length or length. Okay, now let's generate the populations. The population, in this case, we are going to call the function generate population, pop size, and max length. Okay, okay, here we are going to trace through the generations. For each generation, we are going to select parents and crossover the parents by combining the first half of parent 1 and parent 2, and also randomly change the individual, and finally uh, find out the best fitness in the generation and the best solution of the genetic algorithm. Okay, for every generation in. Okay, so let's for parent 1, parent 2, and call the select parents and pass the population into this parent. Okay, the population is generated here randomly, and now select the parents from that population, and the next is applying the crossover, that is the child crossover, and pass parent 1 and parent 2. This is going to combine the first half of the parent 1 and parent 2, and now mutate, and here we pass the child, the individual, and we are going to append each individual into the population. Okay, okay, now we are going to sort based on the fitness score. Sorted, the key lambda x fitness, here we pass x, and reverse is true. Here we just slice up to the top size. Okay, and let's print out the best here the best fitness in each generation would be the generation plus one, the fitness and population at index 0. Okay. Okay. Now finally, let's print out the best solution. And the function going to return the best population at index 0. Okay, let's run this code. Let's make sure that if there is no error. And the last step is running the program, and let's see the best solution from the uh, initial population. The best solution is called that genetic algorithm, and we specify population size, for example 10, and generation is 5050. The maximum length is 10. Okay, let's print this final best solution. Okay, generations, sure. Let's run this code and let's see. Yeah, generation 1, the best fitness in generation 1 is 1, and best solution is 8, 3, 10, 2. So this is the Fibonacci sequence. At generation 2, the best fitness is also 1. At generation 4, the best fitness score is 2, and so on. So it's generate up to 5050 generation, and the best fitness in generation 50 is 3. The best solution is this one. The final best solution is 812240. So this is what genetic algorithm is, and we just find out the best solutions from the initial populations. So as you can see here, initial populations, then select the parent 1 and parent 2 from the initial populations. From that, we cross over the first half of the parent 1 and second half of the parent 2, and mutate the parents, I mean the childs, and also finally get the better population from this initial population. This is what a genetic algorithm is. I hope you enjoyed this video tutorial. If you enjoyed this video and wanna see more fun coding projects, don't forget to like, subscribe, and hit the notification bell so you never miss out an update. Drop a comment below if you have any questions or if you would like to see more beginner friendly tutorials. happy coding, and I will see you in the next video.